Hello guys, nice to see you. Hope you're doing well.
Good afternoon.
Good afternoon. Hello. Hi everyone. So last time we discussed the origins of magnetic field. So we considered some conductor with electric current flowing through it, and learn how to calculate magnetic field in the space surrounding this conducting element. And today we will continue also considering options for determining magnetic field of different current configurations, applying so-called Ampere's law. So we will introduce this Ampere's law, and we'll consider also magnetic field inside a solenoid, and we'll see how it goes with time. Probably we'll also discuss, like, introduce a new parameter, which is flux of magnetic field, but we'll see how it goes, if we can manage to do it today. Okay, let me then switch to our slides. Oops. Actually, okay. So let's start from Ampere's law. And in order to do that, we will consider some configuration of current and magnetic field. So let us assume some conductor, some wire with electric current I flowing through it. So it will create magnetic field around this conductor, and we can consider some displacement ds in the direction of magnetic field vector, so that ds vector is parallel to magnetic field vector. So in this case, let us try to calculate the line integral for this closed path, which we marked with dashed line, of a dot product b vector times ds vector. So assuming that we have this circular symmetry around the conductor, and that shares also, like the distribution of magnetic field also shares this circular symmetry, we can take this magnetic field out from the integral, because it is constant, so it doesn't change. And also, of course, we take into account that these vectors are parallel. That's why instead of vectors in this product, dot product, we can consider just product of their magnitudes. So that will be like integral along this path, just magnitude of magnetic field times ds. And this magnitude of magnetic field, according to this circular symmetry, is constant. So we can take it out from the integral. That will be b times integral ds. And we know from our previous discussions what will be magnetic, like magnitude of magnetic field at some distance r from the wire, straight wire with electric current. So we can write here for magnetic field magnitude mu naught times I divided by 2 pi r. And for this integral along the path over ds is nothing else as the length of this circle. So that will be 2 pi times r. So it will be mu naught I over 2 pi times r. And here in like this integral will be equal to 2 pi times r. Because it's nothing else, this integral as the length of this circle. So taking this into account, we cancel out this, our denominator with numerator parentheses, and eventually we get mu naught times I. So this is actually true for all cases when we have any type of current flowing through a closed path, like some loop. So we can write in general that integral for a closed path of scalar product of magnetic field vector and displacement vector along this path which we choose should be equal always to mu naught, which is magnetic permeability of free space, times electric current which flows through the kind of surface of this closed path. So this is the surface here, and through this surface we have this current I which is flowing through this surface. So means if we know current which flows through the surface of closed loop, we already can calculate this integral. So that is similar, if you recall, when we discussed Gauss law for electricity, we found that the flux of electric field through some closed surface is defined by magnitude of electric charge which is enclosed in this surface. So if there is no charge, there will be zero flux. So that is very useful approach for calculating electric field, like Gauss law, Gauss electrical law. In the case when we have some symmetrical charge distribution. So we did all those derivations for different equations which quantify magnitude of electric field next charge distributions which possess certain level of symmetry. Ampere's law, as similar to Gauss' law in electricity, is also quite useful approach to determine magnetic field next to different current distributions. So let us consider one example how we can apply Ampere's law in order to determine magnitude of magnetic field. So let us assume that we have a conductor straight conductor with some cross-section radius, capital R. So we are interested now to determine magnetic, like magnitude of magnetic field. In two positions. Like first one, somewhere outside the conductor. So we will pick up this closed path with some radius R, which is larger than the radius of the conductor, the cross section of the conductor. And also, so let's call it closed path 1. And also we can pick up some smaller closed path. Let's call it number 2, which has radius R, and this R is smaller than radius of the conductor. So with these two closed passes, we can determine magnetic field outside the conductor and inside the conductor. So let us try first with the bigger closed loop, closed path, number 1. So in this case, we can write that integral over this closed path, let's call it closed path number 1, of scalar product B vector times ds vector, assuming also the symmetry, like circular symmetry, B vector is parallel to the S vector. We can write that this will be equal to B times integral over this path ds. And this is over closed path 1. This will be equal to B times 2 pi r, which is the length of the closed path 1. And according to Ampere's law, we know that this should be equal to mu naught times I, electric current which flows through this conductor. So let us show it here. There is some current which flows through this conductor. If we solve now this equation for magnetic field, it will be mu naught times I divided by 2 pi r, assuming that r is larger or equal to the radius of the cross section of this conductor. So that is actually the equation which we got for magnetic field created by current flowing through a straight conductor, like some wire, by doing like determining contribution to the magnetic field from small segments of this long wire and integrating it all together. So that was quite a challenging task in order to realize this derivation of this equation. However, by applying this Ampere's law, it is possible to get the result in quite simple and straightforward way. So similar to Gauss' law in electricity, it can be very helpful. So now let us consider the second case when we are interested in magnetic field inside the conductor. So for this case, we need to determine which current will flow through this surface of the second closed path. The thing is that when we have first closed path with the radius larger than the radius of the cross section of the wire, it does not matter to us because we know that all current which flows through the wire will flow also through the surface of the first closed path. However, the second one is smaller than the radius, like than the cross section of the conductor. And that means that only a fraction of this current I will actually flow through the smaller closed path, like surface of the smaller closed path. Now, let's say we can write that I prime, it will be some current which actually flows through this surface of closed path 2. And obviously it will be smaller than total current I. And we can write that the ratio I prime divided by I will be actually equal to the ratio of the areas of the total cross section of the wire and area of the surface of the closed path number 2. So assuming that the current density is uniform and current is uniformly distributed all over the cross section. So in that case, we have pi r squared, which is area of the closed path number 2, divided by area of the cross section of the wire. So we can cancel this pi and eventually we can write that I prime is equal to r squared divided by r squared times I. So that is how we can determine total current flowing through the surface of second path. If we operate in terms of the radius r of this circular closed path and radius of the cross section of the wire. So once we know the current, we can proceed further and apply again this Ampere's law. So again, integral over path 2 of scalar product B vector ds vector will be equal to B times 2 pi r will be equal to mu naught, and here is I prime. So instead of I prime, we can write down the following. So it will be mu naught times r square divided by r capital square times I. So once we have this, we can express magnetic field. So here we can cancel out this r and this square. And eventually we will get the following. Let's write it here. Magnetic field B is equal to mu naught times I divided by 2 pi, not this r, 2 pi capital R square times R. And this is valid for the case when R is smaller than radius of the cross section of this wire. So this is equation which describes magnetic field dependence on radius, on position with respect to the origin, like center of this wire, inside the wire. And this equation is valid when we consider already space around the wire, which is outside the wire. If we plot now some dependence of magnetic field as a function of this radius, we will see something like this. Let me maybe delete this. We don't need it anymore. So let's consider we want to plot magnetic field B versus R. And so here will be the center of the wire, 0. Here will be capital R, the radius of the cross section of the wire. And if we now look at first equation for the case when we have R smaller than the radius of the cross section, we see linear dependence here. So magnetic field will linearly increase with increase of distance from the center of the wire. So we can show here a straight line. This straight line will go until it reaches the surface of the wire. And once we go further, like the outer space, already another equation will start working for magnetic field. And here we see that magnetic field is reversely proportional to the radius. So this will look something like this. So it will decrease as distance from the center of the wire will increase. So here we have magnetic field proportional to R. And here magnetic field is proportional to 1 over R. So that is how we can determine magnetic field either inside or conductor by applying this Ampere's law, which plays a role similar to Gauss' law in electricity in terms of its possible application in order to determine magnetic field next to different current distributions. So let us now go for consideration of the next topic, and that is magnetic field in a solenoid. So let me try to share with you my screen. Okay, so solenoid is a long wire in a form of a helix, which consists of several coils, and because of its specific current distribution inside solenoid, it is possible to create quite uniform magnetic field inside the solenoid, because it originates from contributions from each of these turns in the solenoid. So we kind of enhance magnetic field inside the solenoid, and we get quite decent uniformity of this magnetic field, specifically if this solenoid is quite long. So when the length of solenoid is much larger than the radius of solenoid. So something similar in terms of magnetic field distribution we obtained for permanent magnets. We also have more or less uniform magnetic field in the central region of permanent magnet, and solenoid magnetic field distribution has some similar features, but we can really create very strong magnetic fields because of this specific current distribution in solenoid. So our goal will be to calculate magnetic field in in a solenoid. So for this purpose, let us go to next slide. We have such sketch of a solenoid with magnetic field inside. We would like to consider a closed rectangular loop, which is shown here with sides 1, 2, 3, and 4. So the length of this loop will be L and the width W. So now we can apply Ampere's law in order to determine magnetic field inside solenoid. So we see that sides 2 and sides 4, so sides 2 and 4, they are perpendicular to magnetic field vectors. Taking this into account, we remember that in Ampere's law, we deal with the scalar product of when we have this path ds along side 2 and along side 4, they will be perpendicular with magnetic field vector, so there will be no contribution to the integral from these sides. So there are two more sides. There is side 1, which gives us parallel orientation of this side with magnetic field vector. That is important. And side 3. What is important to underline here that the most contribution, the dominant contribution to the integral along closed path will originate from this side 1, because here magnetic field is much stronger than outside the solenoid. So we can just neglect with this contribution to the side 3, and eventually taking into account this consideration, we can write the following. Let me stop sharing the screen. We can write that integral over this closed path for magnetic field vector dot product ds vector will be equal to magnetic field times L, length of the segment of this closed loop with number 1. Element with segment number 3 is located outside the solenoid. Magnetic field is weak there, so its contribution is negligible. So we can write this. And now, if we come back again to the image, we need to know, in order to apply Ampere's law, what is the current which flows through the surface of the loop. The magnitude of electric current which flows through the solenoid is I. However, we see, because of this repeating turns like coils of the solenoid, that we have multiple times this current goes through this surface of the closed loop. So we have once, twice, like 3 times, and so on. So means we need to take into account each time current flows through this surface of the closed loop and sum it up. So that's why, taking this into account, we can write that this should be equal to mu naught times n, its total number of times when current together with the wire goes through the closed surface of the closed path, times magnitude of electric current through this wire. Because keep in mind, there are many turns, but this consists of a single wire. We just make turns of the same wire. Means in any cross section of this solenoid, like wire in this solenoid, electric current will be the same. It will be I. But it goes through this closed surface n number of times. So now we can look at this equation and determine like magnetic field inside solenoid as mu naught n over L times I. So n over L gives us the number of turns per unit length. So we can denote this with small n, and it will be mu naught times n times I. So that is the expression for the magnitude of magnetic field inside the solenoid. Account the current distribution provided by solenoid configuration. which we can easily determine by applying this Ampere's law approach. Now, let us introduce one more, also very important concept in magnetism. And in particular, we can call it Gauss law in magnetism, or just flux of magnetic field through some surface. So let us assume some arbitrary shape body with some surface. We will consider some small surface element dA with the area dA. Then let's assume here we have magnetic field vector B. And this will be vector dA. So as you remember, this dA vector is vector which goes, which defined or its orientation is defined by the normal to the surface, and its magnitude is equal to the area of this surface element. So there will be some angle theta between these two vectors. So magnetic field flux will be defined as scalar product of these two vectors. So will be dFB equal to B vector dot product with dA vector. So it will be scalar quantity, obviously, because we have dot product of two vectors, which gives us scalar quantity eventually. And when we can also write that it will be magnitude of magnetic field times dA and times cosinus theta. So units for magnetic flux, these are Tesla times meter square, and is named by Weber. So we have special unit for magnetic flux, which is Weber. So now let us consider magnetic flux through a rectangular loop, like frame, next to a straight conductor with some electric current. So we have conductor with some electric current I. Then here we will have magnetic field lines, which from this side will go into the surface of the plot. Here we consider our rectangular frame with length, call it B, and width A. So we can write that total magnetic field flux FB will be equal to integral over all surface of this frame of scalar product B vector dA vector. Since in this case magnetic field vector will be parallel to the dA vector, to the surface of the loop, we can write that it will be just integral of magnitude magnetic field vector magnitude times dA. And we know the magnitude of magnetic field vector next to a straight wire, a conductor with electric current, that will be equal to mu naught times I divided by 2 pi r times dA. Now we need to determine dA in terms of r, because we have here this radius r, and we need to somehow determine in terms of r also this small surface element of this frame. So what we can do, let us consider such a strip at distance r with the width dr, and length of this strip will be b. So in this case, we can substitute dA with the product of b times dr. So that will be area of this small narrow strip within the considered frame. So that will be equal to integral mu naught times I divided by 2 pi r b times dr. So that is instead of dA. Now we can take out from the integral everything besides r, because all other parameters are constant, only radius is changing. Will be mu naught times I divided by 2 pi r. Sorry, r should stay on the integral. 2 pi in the denominator, and okay, let me write again. Mu naught times I times b, because this is the height of this frame, divided by 2 pi. And here will be integral dr over r. And this integral should be in some ranges. Any ideas what will be the range for our integral here? So we need to start from this point and go all over to this point. So let us assume that this distance from the conductor to the frame, to left side of the frame, let's denote it as C. So then our radius will change in order to cover all surface of this frame. We need to go from C to C plus A, which is the width of the frame. So it should be C here, and C plus A the furthest point until which we need to integrate. So let me rewrite this integral on the next slide. So we have some space. It will be magnetic field flux will be equal to mu naught times I times B divided by 2 pi integral from C to, say, A plus C dr over R. So this integral will give us natural logarithm of R. So it will be mu naught times I times B divided by 2 pi times natural logarithm R from C to plus C. Now we get mu I times times B divided by 2 pi. And here we have natural logarithm of A plus C minus natural logarithm of C. Considering the features of logarithm, we can write that mu naught I B divided by 2 pi times natural logarithm of A plus C divided by C. Or it will be like final form for our equation, mu naught I B divided by 2 pi natural logarithm 1 plus A divided by C. So that is the equation which gives us the magnetic field flux through the rectangular frame placed next to the a wire with electric current. Keep in mind that this integration is necessary because magnetic field is not uniform next to a wire, so it decreases with increase of radius distance from the wire. So that's why we cannot just, if it's just uniform magnetic field, we would have product of uniform magnitude of magnetic field B with area of the rectangular frame, which is A times B, and we would get the flux. However, we need to assume that magnetic field is changing is different in different point of the surface of this rectangular frame. So that is done by doing this integration, and this is the final result. What is important to highlight that regardless, like we can compare this Gauss law in magnetism with Gauss law in electricity, and we remember that electric field flux through a closed surface depends on how much of electric charges we have inside the, and which sign of magnetic of electric charges we have inside the closed surface. However, for magnetic field, you need to know, since we do not have magnetic charges, we don't have isolated monopolies of magnetic field. We always have two pulses of poles of magnetic field together, north and south pole, and magnetic field lines do not originate and terminate on some pulses. They are kind of continuous. taking into account these features of magnetic field, which is different fundamentally from electric field, magnetic field flux through a closed surface is always equal to 0. So that is the fundamental difference in terms of magnetic field flux in comparison to electric field flux. And that originates from the fact that we have negative and positive charges, and electric field lines originate at positive charges and terminate on negative charges. However, this is not the case for magnetic field lines. They are continuous. Okay, guys, so I see we are running out of time. This is pretty much everything what I wanted to discuss with you today. If you have questions, you're welcome. So we discussed today Ampere's law, which is equivalent to Gauss' law in similar in terms of application to Gauss' law in electricity, because Ampere's law allows us to determine in a simple and straightforward way magnetic field next to different current distributions. So we have shown this on an example of determining magnetic field outside a straight line conductor and inside this conductor. Also, we determine by means of Ampere's law magnetic field inside a solenoid, which is consists of a single wire, but is made of repeating turns like coils of this wire. So that's the current configuration, which can result in quite strong enhancement of magnetic field in the internal area of the solenoid. And also we introduced the concept of magnetic field flux and have shown this on how to determine it on the example of magnetic field, calculating magnetic field flux through a rectangular frame placed next to a straight conductor with electrical current, assuming that spaced non-uniformity of magnetic field next to a straight conductor with electric current, we could get the total magnetic field flux through this rectangular frame. Okay, guys, thank you very much for your attention. Have a good evening and see you next time when we will start considering already electromagnetic induction.
Thank you.
Okay.
Thank you.
Thank you. Goodbye.
Goodbye.
Bye-bye.